decreasing. Or if something is doubling, if something was doubling every year, that would just be a 2, right? Doubling is the same as what percentage? Yeah, like you put a 200 in there. If this can was doubling, what would it say at the top? Well, I wouldn't say, because it sounds better to say it's twice as much rather than say bonus 100%. Like if the yellow part was as big as the red part, it would say bonus 100%. Now twice as big. Anyways, yeah, big long can. So this is this function to model that, right? There's the function that models it. Growing at 4% is a lot different than the thing I showed you before in the spreadsheet. It doesn't grow nearly as fast because the other thing was growing at 100%. We're doubling it, right? So it goes from 1 cent to 5 million in 30 days or whatever that is. This is not going to grow as quickly as that. The graph of the other thing would start like this and it would be off the scale before you even get to the end. This one is going to look more like this. It's going to look a little bit straighter. The smaller the percentage is, the more straight it looks. If you're getting 1% growth on something, whether it's money or population or whatever, it almost looks like a straight line because it's not a whole lot different until you look long term. I do want you to go through and do some of this stuff, but I want to give you enough of a start to do this. I'm over my 10 minutes, so we're just have to keep going, and I'll upload it in 2 parts, I guess. You can use the calculator. I want you to confirm. I mean, part of this is learning to check something graphically and then confirm it. I'm hoping you know how to, using your calculator, find an answer to something graphically. It means find the graph and then use it to calculate a value. Confirming it analytically means, for this, just subbing in the number. I'm not sure how many of you remember how to solve for the exponent. Okay, it says when the population, here you're going to need to use logarithms. You're going to have to remember that. If you are taking Math 12 right now, ask me and I'm going to help you. The second question that I give you here is a compound interest thing. There is a compound interest formula. So you're going to work on this in a minute here. There is a compound interest formula, but I prefer to just think of it from first principles and set it up. If you're compounding something annually, this is no different than population growth. What would the function here look like? You have $1,600 to start, 5% per year. So what's it going to look like? Absolutely, right? 1.05 to the power of t, time in years. The only difference here is if it's semi-annually, or monthly, or weekly. Do you know how that affects it here? Yes, you do. What's the function going to look like if we change this to semi-annually? I guess I could have picked a better number other than... I'm not thinking I want to think in terms of 5, so can I change this to 6? Anybody not okay with that? 6 works better when we get to monthly. I can't do that. I can't change the questions. Well, I made it in the first place, so I can change it. You should change it. Well, if you want to keep it as 5, then you're going to be going 5 divided by 12 and not such nice things. I know that's hard, but... What's the second one here? 1,600. If you compound semi-annually, it means they don't wait the whole year to pay you the interest. Halfway through the year, they calculate how much interest you've made up to then. If you're getting 6%, but you're getting it semi-annually, that doesn't mean you get 6% halfway and another 6%. It means they're going to give you 3%, figure out what that is, in the middle of the year. So you get 103%, but how many times do you get paid that interest? So there's going to be 2t up here, twice as often. Because it's happening twice as often, right? Half the interest, twice as often. Now the next one, since we changed it, is okay here because now it's $1,600. What is it going to be here? Yeah, every month they give you 0.5%. What's the exponent going to be now? How many times is this going to happen? Yeah, 12 times t, right? If you thought about an actual number, right? I mean, if you're actually thinking of this as a number, let's say that this was 5 years. That's actually a 5, believe it or not. If it was 5 years, how many times do you get paid interest if it's compounded annually? You get paid, I'm going to use an n for the number of times compounding. 5 times, here you get 10 times because you get it twice a year for 5 years. Here you get it 12 times a year for 5 years, so you'd get it 60 times. Down here, what did I say, weekly? What's this one going to be? Now this one's not going to be so easy to do in our head, right? But we can write it like this. We can write it as 1 for the original 100% plus whatever 6% is, 0.06, divided by 52, right? Weekly. To the power of 52t. Here you'd get 5 years times 52. You'd get paid lots of interest, right? 260 times, you get paid the interest. Daily, what's our function going to look like? Yeah. Now, you can get daily interest savings accounts, but they don't actually compound it daily. The most often on a savings account there, we're going to actually compound it is monthly. When they talk about a daily interest savings account, it means they'll calculate how much interest you get each day. Like if your balance changes quite a bit and you have $10,000 one day and then you have $5 the next day, and I don't know what's going on in your life if you do, but you'll get different amounts of interest each day, but they don't actually pay it to you till the end of the month. So it's more complicated than that. And then up here, what was this? 365 times however long the time is. What we need to look at here is how does the effect of compounding it, how does changing the number of times you compound it affect what the final result is? And that's what's going to lead us into after talking about the variable e. What? What I want you guys to investigate after is hey, listen. One more minute here. I want you to investigate how does this change based on how often you change the compounding. So what I want you to investigate is this. Really, all we're interested in looking at here when we look for what the number e is this. We want to change this. So we're going to keep things simple here. We're going to use that as, we're going to make the variable the number of times you compound. Okay? We're going to look at the values you get when the number of compoundings is the variable. Okay, you can use x for that. And then y is the final amount. But we're going to keep everything else simple, just like any other experiment. If you're trying something, keep everything else the same and don't change it. So let's say, to keep it simple, when you're investigating this e thing here, we are going to start with, you're going to make the starting amount how much money? $1. Because timesing by 1 doesn't change anything, right? $1 for 1 year at 100% interest. Why do I want to use 100% interest? Because what is that when you write it as a decimal? 1, right? If all the other things are 1, then it's going to be really easy to see what this does. So what we're saying here is make this $1, make this 1 year, because then it's not there, and then make this 100% because it's just a 1. So the only thing that's changing is the thing in blue. You can investigate it with your graphing calculator, set up a table. Try things like, try the different compoundings here and see how the final amount compares. put in, do semi-annually, quarterly, monthly, semi-monthly, whatever. Do a bunch of things. Track what happens to the final amount. That's what's happening here, okay?